Hello, welcome to my presentation where I am going to explain you the topic Introduction to Measuring Instruments and Measurement Errors. My name is Swati Palasa. I am lecturer in Electrical and Electronics Engineering, Sanjay Gandhi Government Polytechnic, Adilabad. So let's first take a look at what is measuring instrument. A measuring instrument is a device for measuring a physical quantity. You must be aware of thermometer. Thermometer is also a measuring instrument which measures the temperature or a temperature gradient. Similarly, we have different measuring instruments to measure different quantities like electrical quantity, mechanical quantity, etc. There are many definitions of measuring instruments. I have put one more definition. It says that the device used for comparing the unknown quantity with the unit of measurement or standard quantity is called a measuring instrument. So it clearly states that measuring instrument is a device which compares unknown quantity with a standard quantity. Now let us see some measuring instruments to measure basic electrical quantities like voltage. Voltage units are volt, and voltmeter, multimeter are the measuring instruments which are used to measure voltage. Similarly, ammeter, multimeter are used to measure current, and the current units are amperes. To measure resistance, units ohm, we use ohm meter, multimeter, LCR meter. Multimeter is a meter, the measuring instrument. It's a digital one. We can have analog multimeters also. It is a measuring instrument which is used to measure different quantities using the same instrument, the same device. And LCR meter is also a single device which can be used to measure inductance, capacitance, and resistance. That's how the name comes, LCR meter. Now, capacitance is an electrical parameter with measuring unit farad. Multimeter and LCR meter can be used. Similarly, LCR meter can be used to measure inductance also. Units of inductance is Henry. Now, power can be measured with the help of wattmeter. The units of power is watts. We have different measuring instruments to measure frequency of the supply or a signal. Units of frequency is hertz. Frequency meter is one of the meters which can be used to measure frequency. Similarly, energy meter is used to measure energy. Units of energy is watt hour or kilowatt hour. Everybody must be having a meter box outside the house which includes energy meter. Energy meter records Number of units consumed by the house. Now, when we are learning about the energy meter, we need to assess the performance of measuring instruments like energy meter, as we have discussed earlier. The characteristics of measuring instruments are specified using terms. Few terms are as below. So these terms are true value. True value is a standard or a reference of known value or a theoretical value. Standard or reference. That means true value is an absolute value. The next term is accuracy. Accuracy is defined as closeness to the true value, closeness with which an instrument reading approaches the true or accepted value of the variable being measured. Suppose I'm having a load. So here we have a load. Load is connected to a huge circuit here. I want to measure voltage across this load. For that, I'll be using a voltmeter. Now, I know the voltage across the load already. Say the theoretical calculation says that, or the true value is, it says that the load voltage is 230 volts. But now, when I want to measure the load voltage, I'm placing a voltmeter across the load. And when I check the meter reading, say it is saying 229.2 volts. That means this 229.2 is really very close to 230, which is the true value of the voltage. But the measured value is 229.2. It's actually very, very close. So with that, we can say that this meter, voltmeter, is an accurate meter. If the voltmeter has shown 220 volt, then accuracy is very, very, very less. It may not be in acceptable value range. So let us go for the next term, which is precision. A measure of reproducibility of the measurements is precision. Given a fixed value of a variable, precision is measure of the degree to which successive measurements differ from one another. Say, for example, we are in a lab and we are trying to check the functioning of the voltmeter. Same circuit we'll look into. So I am with three of my friends. So first I tried checking out the voltage across the load and I got the reading of 229 volts. Next, my friend tried it for the second time. She again plugged in the voltmeter and checked the readings of the voltmeter, and it is again 229 volts. And for the third time, my friend, another friend, she tried it and it is again 229. So this is how, whatever be the number of times you use the meter for same work, same quantity, it should be exhibiting the same value. That means the meter is a precise meter. So it is able to reproduce the measurement again and again. Even though we tried for multiple trials, it is showing the same reading or nearly same reading within an acceptable range. That is what we call as precision. Now, so far in this slide we have seen different terms: true value, which is a standard value, which is a known value, it's a theoretical value, it's an absolute value. Now we'll go for another terms like sensitivity. Sensitivity is the ability of measuring instruments to respond to changes in the measured quantity. It is expressed as ratio of output signal or response of the instrument to change of input or measured variable. It is like this. Suppose we have a current source and I can change the value of the output current. Now I am giving this current source to a network. I am using an ammeter. Now we are trying to discuss the sensitivity of this ammeter. Now my current source is showing it. I can vary the value of variable current source. So yeah, I can vary the value from 5 ampere to say 10 ampere, something like that, like milliamperes. We'll discuss in milliamperes. Now, this is our knob where I can vary the current. Say it is 1 ampere, 2 ampere, like that. Now this is the load. Now when the knob is in 1 ampere, that means the input is 1 ampere. Say the meter is showing around 0.9 ampere. So this is the measured value and this is the input. Now, after a while, I will increase the current. Say this is input 1, this is measured value M1. And my input is changed to input 2. Say it is 2 ampere now. And when I check the ammeter reading, my ammeter is showing say around 1.8 ampere. Now the sensitivity is nothing but it is the ratio of change of output to change of input. The output is measured by the measuring instrument and input is given by the current source here. So sensitivity for this case is going to be change of output 1.8 minus 2 by change in, sorry, it's not minus 2, 1 M2 minus M1. M1 is 0.9. Input 2 is 2 ampere minus input 1 is 1 ampere. So which is going to be 0.9 by 1, or it is 0.9. So 0.9 will be sensitivity. Now let us go for resolution. Resolution is the smallest change in measured value to which the instrument will respond. That is, smallest incremental quantity that can be reliably measured. More is the resolution, more accurate value we get. If you have more resolution for the instrument, we can measure accurate value. Say we have a quantity whose true value is known, and the true value is 1.12. Say it is a current and amperes. Now, if the resolution of the meter is high, it can give meter reading can be 1.11 or 1.12 or like that. This is for good resolution. If resolution is not good, then your meter reading is just going to show 1. This means it's a bad resolution. That means resolution is not up to the mark. So even smallest change in the measured value to which meter or instrument will respond is called as resolution. That means even for 0.12, the meter got responded, and so it has recorded 1.12 or 1.11. Now let us go for another term, error. Error is deviation from the true value of the measured variable. So it is very clear that suppose we have a meter and we have a quantity to be measured. I know the true value of the quantity to be measured. Say the true value is 2 volts. But my meter is showing 1.6 volts. Now error is difference between measured value and the true value. That means 1.6 minus 2. It is 0.4. So 0.4 is the error that meter is showing. So with this, I hope you're clear with the sensitivity, resolution, and error. Let us go to the next slide. Here in this slide, we are going to see classification of errors according to its source. According to its source means why are we getting error? What is the source of error? That's what we are going to see here. So error may come from different sources and are usually classified under 3 main headings as gross error, systematic or determinate errors, random or indeterminate errors. Gross errors are largely human errors. So these gross errors include It may include misreading of instruments or incorrect adjustments or improper applications of instruments and computational mistakes. So, gross error can be any one among these. So, misreading of instrument. Suppose the reading is showing 2 value, but because of parallel error, the reader is reading it as say 1.8. So that 0.2 comes under error, and it is the error because of human who is unable to read it properly without parallel error. So those kind of errors come under gross error. Incorrect adjustment. Incorrect adjustment is like we have zero setting. Every meter, analog meter especially, needs to be set to 0. That means pointer should be showing to 0. If you have an analog meter, say this is the display of the analog meter and here is 0. A pointer should be showing here. But sometimes what happens is pointer will be showing either here or here. So we have to make 0 setting. You will be having a screw kind of screw here, and we have to adjust this pointer to 0 setting using this. So if those adjustments are not made, meter reading is going to be wrong. It is not going to be exact. So those come under incorrect adjustments and also improper application of instruments. Suppose you are trying to measure the current which is in between 0 to 5 amperes, but the meter you are using is capable of measuring 0 to 100 amperes. So this 0 to 100 ampere will be lacking resolution that it measures small current from 0 to 5 ampere. So this is what we call as improper application of the instrument. And computational mistakes. In few meters, we have to calculate the scale of the meters. So in calculations of the scale of the meter, if we make mistake, then the reading that you are going to take is also going to be wrong. So all those kind of errors will come under gross errors. The next error we look is systematic or determinate error. These systematic or determinate error are shortcomings of the instrument such as defective or worn parts and effects of the environment on the equipment or the user. So these type of systematic errors are the errors that are because of the worn parts in the measuring instrument. Now, if we go for electromechanical measuring instruments where we are going to have moving parts, now moving parts will be worn out if it is used for some years. Then when parts are worn out, meter will not work as it used to work when it is brand new. So there is a possibility of error. So that's how the errors which come because of worn parts or defects in the instrument, those are called as systematic errors. And the next type of error is random. Random error is indeterminate error, and these kind of errors are not controlled. We will not have any control over them. Let us see what is random error. So random errors are those errors due to causes that cannot be directly established because of random variations in the parameter or the system of measurement. Here, the parameter which we are going to measure, if it is varying randomly, or the system that you are using for measurement If there are changes in the system randomly, then we are going to get errors, and those errors are called as random errors, and we cannot have any control over them. This is how we have seen three different types of errors: gross error, largely human errors, systematic errors, and random errors. So here we can see the same thing in a schematic figure. This is a summary of errors to some extent in a schematic way. So measurement errors, according to the source, are categorized to human errors, which are gross errors, systematic errors, and random errors. Random errors are the errors whose causes are not known and which are quite random. They are unexplainable. It is random behavior of either measurement system, or it is a random behavior of the parameter which we are measuring. Coming to the systematic error, we have further two types of the systematic error, which is equipment error and environmental error. So whatever the environmental or equipment, it comes under the systematic error. That means the error in the measuring instrument. Coming to the equipment errors, the examples are bearing friction inside the measuring instrument and non-linearity components, calibration error, damaged equipment in the measuring instrument, and loss due to transmission. Coming to environmental errors, we have these errors because of change in temperatures, humidity, strain, electric and magnetic fields, etc. And coming to human errors, these errors are also called as gross errors. These come because of misreading of the instruments, erroneous calculations, improper choice of instrument, incorrect adjustment, or forgetting to zero, neglect of loading effects, etc. These are some examples of human error. Now, let us see the classification of instruments. Instruments are classified to mechanical instrument, electrical instrument, electronic instrument. Now, we are concentrating much on electrical instruments, and in these electrical instruments, we have further classification: absolute or indirect instrument, direct or secondary instrument. And further, secondary instruments are categorized to analog instruments, digital instruments. And analog instruments is further categorized to deflecting type instrument or null deflection instrument. And deflecting instruments, which are used widely, are further categorized to indicating instruments, integrating instruments, and recording instruments. Indicating instruments, integrating instruments, and recording instruments. So this chart shows the classification of instruments. Now, let us see the classification of electrical instruments. Electrical instruments may be divided into two categories broadly. One is absolute instrument, other one is secondary instrument. Now, electrical measuring instruments may also be classified according to kind of quality, kind of current, principle of operation of moving system, etc. That means you have few measuring instruments that are used only to measure DC currents or DC voltage. And you have few measuring instruments that can be used for both DC as well as AC. And like that, we have different categories. So let us look at the details of absolute and secondary instruments. Absolute instruments give the quantity to be measured in terms of instrument constant and its deflection. They do not need to be calibrated and do not need any comparison with other standard instruments. Now, when we try to construct a meter, we need to calibrate generally. That means, suppose I have constructed a meter like this. Okay, this portion is dial or a display portion. I am having readings here and I am having a pointer. Say these are the terminals to which I have to connect. Now suppose I connect it to some value, the pointer will be deflecting. Pointer will be deflecting to some other value. Now, how should I know? When I don't connect any electrical quantity to the meter, pointer is at state of rest pointing like this, say. That means this value should be equals to 0. Now when I give some quantity whose true value is known, say this is an ammeter, so I give 1 ampere of current, say, then pointer is showing, say I will change the color to green, say the pointer is showing this one, and we know that we have connected 1 ampere to it, that means it is going to be 1. Actually, what are we trying to do here? We are trying to give values to this scale, how the pointer is deflecting. This process is what we call as calibration. Knowing the true values of the input quantity, we are trying to compare the values and how the deflection of the pointer is, and then we are marking the point of deflection as the true value. This procedure is what we call as calibration of the meters. Now, the absolute instruments do not require calibration. This is very important point. It do not require calibration, and absolute instrument will give the quantity to be measured in terms of instrument constant and its deflection. This is very important point to remember. So because they don't require calibration and because they give the quantity to be measured in terms of instrument constant and deflection, they are used in library as standardizing instrument. They are standardized instruments and they are used for calibration of other meters. Examples of absolute instruments are tangent galvanometer, absolute electrometer, relay current balance, etc. Coming to the secondary instruments, in secondary instruments, the deflection gives the magnitude of electrical quantity to be measured directly. So here it is just like the box that we have drawn. So we say that this box is an ammeter. Now when I give 0 amperes of current, it was showing this way, so we have calibrated it as 0. And when I know the true value of the input current and when I give as 1 ampere, the pointer was showing to green mark, and it was calibrated to 1. It was marked as 1 ampere. Similarly, if you give 2, it is going to this red mark pointer. So say it is going to be 2 ampere. This is how we are going to calibrate the instrument. So this kind of instrument is what we call as secondary instrument. So this is secondary instrument. As we are calibrating this. So to calibrate this type of secondary instruments, we take help of absolute instruments. So this secondary instrument will deflect and it will show the magnitude of the electrical quantity to be measured directly. That is why we call these type of instruments as direct instrument. Now these instruments are required to be calibrated by comparing with another standard instrument before putting into use. These instruments need to be calibrated against absolute instrument because absolute instruments are considered as standard instruments. Now, the applications of secondary instrument is in everyday work. The ammeters, voltmeters, ampere hour meter, watt meter that are used in everyday life, that are used in laboratory, that are used near meter box, at agricultural motors, everywhere the meters that are used are secondary instruments. So in this slide, we have seen what is absolute instrument and what is secondary instrument, and we have seen the difference between absolute instrument and secondary instrument. Let us go to the next slide where we are going to see the classification of secondary instruments. Secondary instruments can be classified into 3 types. One is indicating instruments, another one is recording instruments, the next one is integrating instruments. What is indicating instrument? Indicating instruments indicate the magnitude of the electrical quantity at the time when it is being measured. Indications are given by pointer moving over graduated dial as shown below, like this. So this is what I have drawn in the earlier slides. This is the display and this is the pointer. Pointer will have deflection from this point to this point. And here you can see a mirror in this gap. You can see a mirror in this gap. That mirror is placed to reduce the parallax error while taking the readings. Human error, gross errors. Reason for one of the gross errors. And this is the pointer. And these are the terminals where we are going to connect the meter in the circuit. Now, this is the pointer. You can see here. Pointer. This is mirror. These are readings. It's a graduated dial. This is what we call as a graduated dial. And these are the terminals. Let us go for next type of instrument, which is recording instrument. Recording instrument recording instrument is an instrument which keep a continuous record of the variations of the magnitude of an electrical quantity to be observed over a definite or a defined period of time. Which means, as we have seen in the previous slide, we have seen that indicating instrument will have deflection of the pointer only when it is connected to the quantity to be measured. When it is not in the circuit, it will come back to zero position. It will no more indicate the value to be measured. But the recording instruments will keep a continuous record of the variation of the magnitude of the electrical quantity to be observed, which means it will have a record of the previously measured quantity and how it is varying now. This is what we call as recording instruments. Suppose we are trying to measure frequency of a supply. So I am trying to measure a frequency of a supply. Generally in our country, we will use, for domestic purpose, we will use around 230 volts single phase for normal domestic purpose. We will use 230 volts single phase 50 hertz supply. All of our applications are rated to 50 hertz power supply. They will work for 50 hertz power supply with certain tolerance rate of 5%, which means 5% of 50 hertz. Say for example, it is nearly around 47.5 to say around 51 hertz. Just an example. This is the tolerance duration tolerance range where the change in frequency is acceptable for our applications. In such case, where the quantity monitoring is very important, there we can use a recording instruments. These recording instruments will keep a track of previous values. Say for day 1, the value is 48 hertz. And for day 2, the value is 49 hertz. So the recording instrument will memorize the day 1's data and it will compare with day 2's data and it will try to calculate the difference, variation, and we can have different alarms accordingly. So this is the duty of recording instrument. Another type of instrument is integrating instrument. Integrating instrument are the instruments which measure total amount of either quantity of electricity or electrical energy supplied over a period of time. The best example of integrating instrument is energy meter. Integration means it tries to integrate more than one quantity. It tries to multiply, add on, something it does with more than one quantity. If we take an example of energy meter, where energy means it has to integrate power and also time. It has to integrate power and time. So it does that and hence it is called as integrating instrument. So best example of integrating instrument is energy meter. So this is how we have seen different types of secondary instruments. So we have seen different types of secondary instruments, which are indicating instruments, recording instruments, and integrating instruments. Now let us go to next slide, where we are going to integrating instrument. Here you can see this is an energy meter. Energy meter. This is the disc. You see this kind of energy meters in old established houses, not in new constructed houses. Nowadays, we are not having analog energy meters. We are all having digital energy meters. Analog meters mostly are replaced by digital meters, but still there is importance of analog meters, considering a lot of positive points of these meters, like cost is low. It is going to show correct value. There are some disadvantages with digital meters, which we are going to see in our future videos. So we'll have a quick recap of all our slides now. Let us just have a quick recap of all our slides. So we have seen introduction, and we have seen the definition of measuring instrument, and then we have seen different electrical quantities and what are different meters that can measure these electrical quantities. And we have seen few terms which are used to specify the characteristics of measuring instruments. Those are true value, accuracy, precision, sensitivity, resolution, and error. And we have seen what are all different types of errors, classification of errors according to its source. We have seen that instrument errors are categorized to gross errors, systematic errors, random errors. We have seen each and every error along with examples. And then we have seen classification of instruments. Here we have classification of instruments based on quantity to be measured, mechanical, electrical, electronics, and broad classification of electrical measuring instruments. This is the basic classification. Absolute instrument or secondary instrument. And then classification of secondary instruments, analog instrument, and digital instrument. This is classification based on the output and based on the working. And then we have seen Further classification of analog instruments, deflecting type and non-deflecting type or null deflection type. Then under deflecting type, we have further classification to indicating, integrating, and recording type of instruments. And we have seen what is an absolute instrument, what is a secondary instrument, and distinguish. We are able to distinguish absolute instruments with secondary instruments along with their examples. Then we have seen classification of secondary instruments. What are indicating type of instruments? What are recording type instruments? What are integrating type instruments? So this is indicating type instrument. Only when I give signal, the pointer will deflect. If I don't give signal, pointer will come back to 0. The meter will not have any memory. It will not keep track of previous data. And that is how we call it as indicating instrument. Only when we connect the meter to the quantity of to be measured, then only the pointer will deflect. And then we have seen recording instrument. Here we have a digital or an electronic instrument with a digital display. This will have track of the data. So we use it for recording purpose, for monitoring purpose especially, we use recording instruments. And then integrating instruments. Best example of integrating instruments is energy meter. This is going to integrate, energy meter is going to integrate power with time. So power into time. It actually gives energy it will give this value, power into time. This integration it does. This simple meter will do this much of math and hence it is called as integrating instrument. So best example of integrating instrument under electrical measuring instruments is energy meter. So the optimistic learning outcomes of this presentation is students should be able to define measuring instrument. You should be able to list important electrical quantities to be measured by giving their units. You should be able to name the instrument to be measured, to measure various quantities. You should be able to define accuracy, precision, error, resolution, sensitivity, and classify errors according to its source, classify instruments based on construction and output, and classify electromechanical instruments according to principle of working, and classify instrument based on method of measuring the value, like absolute and secondary, and distinguish between absolute and secondary instruments, state different types of secondary instruments with suitable examples. Thank you for listening patiently.